Hello friends, welcome to Engineering Funda family. In this video, I'll explain you RC phase shift oscillator in complete details. Before I start with explanation, let me show you how many things that I'm going to cover in this video. First of all, I'll be explaining you basics of oscillator. After that, I'll explain you RC phase shift oscillator using operational amplifier. So this is the basic circuit with which one can have RC phase shift oscillator. RC phase shift oscillator that can be also deployed using transistor, but here I'll be explaining that with respect to OpAmp over here. And at last I'll be going to derive feedback gain calculation by which you can understand how exactly oscillator functions. So let us begin this video with first agenda, that is basics of oscillator. Oscillator is used to generate sinusoidal waveforms. Let me explain you how. See, oscillators are used to generate low frequencies up to few hundreds of kilohertz. Using positive feedback, one can generate sine wave using oscillator. Here basic block diagram that is shown for oscillator, in which here we have amplifier that is having gain A, and here we have feedback that is having gain beta. We use positive feedback. So here in feedback, polarity will be positive over here. To have oscillation at output side, there are two criteria that you need to understand. See, first criteria states that A into beta that should be equals to 1. So multiplication of gain A into beta that should be equals to 1. And second criteria states that phase shift of A and B should be 0 or 360 degree. Here we will be providing phase shift of 360 degree. Let me explain you how. See, here we will be having amplifier. This amplifier will be generating phase shift of 180 degree. Means here input will be having some signal and output will be out of phase with respect to input. And here we will be using feedback. This feedback will be also providing phase difference of 180 degree. So in total, at output side, 180 plus 180 means 360 degree phase difference will be there. And if you have this criteria, that is A into beta is equals to 1 and phase shift of 360 degree, then sine wave can be produced over here. Now I'll explain you how one can have oscillation using RC phase shift oscillator. Here you can observe basic circuit diagram of RC phase shift oscillator using operational amplifier, in which this much portion of circuit that belongs to amplifier using OpAmp and this much portion of circuit that is there because of feedback. Here if you observe amplifier portion, then with amplifier portion we are using OpAmp in inverting mode. In inverting mode, gain of this OpAmp that will be happening as per minus RF by R1. And here as we are using this OpAmp in inverting mode, phase shift provided by this OpAmp that will be of 180 degree. Here you can observe feedback circuit as per RC combination. With this RC combination feedback, gain will be beta. Here A into beta that should be unity for oscillation condition, right? I have explained that. See, for oscillation condition is A into beta that should be equals to 1, right? So that is the basic condition. Here I'll be going to derive each and every equation, but let me tell you how many things that we need to understand over here with RC combination. See, we will be going to derive this gain beta that will be 1 divided by 29. And as beta is 1 divided by 29, this A should be 29 over here. In that situation only, A into beta that will be equals to 1. And this feedback that will be also providing phase shift of 180 degree. The reason is 180 degree phase shift that is provided by this amplifier. And as if this feedback is also providing 180 degree phase shift, then 180 plus 180 means 360 degree phase shift will be there. That is the basic condition for oscillation, right? So this feedback circuit that will also provide 180 degree phase shift. So here, if you select this RC combination in such a way that gain is 1 by 29 and A is 29, in that case there will be oscillation, and here oscillation frequency will be, if I say it is F, then that will be 1 divided by 2 pi RC into square root of 6. Here if you observe, see here we have RC combination, and with this RC combination we are having 3 stages of RC, and for 3 stages of RC frequency is 1 divided by 2 pi RC into square root of 6. If you have n number of stages of RC combination, in that case your formula will be F is equals to 1 divided by 2 pi RC into square root of 2n, where n is number of stages of RC. Now I'll explain you how this gain is equals to 1 by 29 and how this frequency F, that is equals to 1 divided by 2 pi RC into square root of 6. So these equations that I'm going to derive now step by step. Now I'll explain you calculation of feedback gain. Here you can observe this is the feedback circuit which we have connected over here, where you see with this OpAmp we are providing feedback over here. So this is V out, and here we have feedback voltage. So if you compare that circuit over here, then you see here we have V out, that is written over here, and we have feedback voltage VFB, that is over here, right? So here we have CR connection like this, and at this terminal we have feedback voltage. Our agenda is to calculate feedback voltage divided by V out voltage, and that will be 1 by 29 that I'm going to derive over here. So for that calculation, first of all I'll be considering nodal voltages over here. Let us say here voltage is V1, and let us say here voltage is V2. Let us say through this capacitor current is I1, through this capacitor let us say current is I2, and through this capacitor let us say current is I3. So but obviously through this R current will be I3 only, as it is there in series with this. But through this R we need to assume current. Let us say it is I dash over here, and over here it is I double dash. Now to have derivation of VFB divided by V out, I'll be starting solution from this side. So to solve this circuit from this side, I'll be considering V2 voltage calculation first. So as per this branch calculation, let us calculate V2 voltage. So here what is the value of V2? See, this V2 will be this I3 into impedance of this capacitance. So V2 is I3 into XC over here plus I3 into R. But this I3 into R, that is VFB voltage. So I'm writing VFB instead of I3 into R. And I3 into R, that is VFB, right? So what is I3? I3 is VFB by R. So let us write that over here even. I3 is VFB divided by R into XC plus VFB. So here let us simplify this further. So VFB, that is common, and here we have 1 plus XC divided by R, right? So now we have V2 voltage. Now to solve this circuit, we will be going in this direction. So now we need to find what is the value of I2 current. To get the value of I2 current, we will be applying KCL at node V2. So entering current, that is equals to leaving current. Entering current is I2, and leaving current, that is I3 and I dash. So here leaving current is I3 plus I dash. Now what is the value of I3? I have told you I3 is VFB divided by R. So I3, that is VFB divided by R. And what is the value of I dash? I dash is V2 divided by R. I dash is V2 divided by R. Here we have calculated V2 voltage, that is this. So we need to substitute that over here. So VFB divided by R plus This V2 is this. So let us substitute it over here. Now let us simplify this equation further. So let us take VFB common over here. So now we will be having, you see, 1 by R and 1 by R means 2 by R over here, plus here we have XC divided by R square, XC divided by R square. So now we have I2 value now. Now in this circuit, we have V2 and I2. Now we need to have V1 value, right? To get the value of V1, I'll be applying potential difference in between this capacitor. So that is V1 minus V2. So here we will be having V1 minus V2, that is equals to I2 into XC, right? V1 minus V2, that is equals to I2 into XC. Based on that, we can have V1. So here, what is the value of V1? V1 will be, this V2 will go on other side. So V2 plus I2 into XC. Now you see, we have V2 as well as we have I2, that we can substitute over here and we can have the value of V1. So let us substitute V2, that is this, and let us substitute I2, that is this. Now we need to simplify this equation. So I'll be taking VFB common. So if you take VFB common, then we will be having parameters inside. See, here we have 1. So let us write 1 over here. We have considered this. Now we have XC by R over here. And here if you observe, XC is getting multiplied inside with 2 by R. So 2XC by R plus XC by R will be 3XC by R over here. So we have considered this 2 and this. And plus we need to have XC into XC by R square. So that will be XC square by R square. So now we got the value of V1. Now once we have the value of V1, we need to find the value of current I1. So to get the value of current I1, we will be applying KCL at node V1. So here at node V1, entering current is equals to leaving current. Entering current is I1 and leaving current is I2 and I double dash. What is the value of I double dash? I double dash, that is V1 by R. And what is the value of I2? I2 we have calculated over here. You see, that is this. So let us substitute this over here. Now in this equation, we need to substitute value of V1 even. So V1 is this, right? So I'll be substituting V1 in this equation. Now we need to simplify this equation of I1, right? So for that, let me explain you how to simplify that. So here I1 is, you see VFB, that is common. I'm taking it over here. Then I'll be considering terms one by one. So you see here we have 1 by R and here we have 2 by R, right? So that is 3 by R. So I have considered these two terms. Now you see here we have 3XC by R square. And here we have XC by R square. So 3XC by R square plus XC by R square, that is 4XC by R square. Now here if you observe, we have XC square by R cube, as we need to divide this R over here, right? So here we have XC square divided by R cube. So that is how now we are having value of current I1. Now we need to see this circuit. Now we have I1 as well as we have V1. So now we can have V out by taking potential difference in between these two terminals. So let me write that first over here. After that, I'll be writing that below, right? So here, if you consider calculation of V out minus V1, so that will be I1 into XC. Now with this equation, we need to have V out, right? So V out, that will be how much? V1 plus I1 XC. We have calculated value of V1 and I1, right? You see V1 is this and I1 that is this. So let me take this calculation below. So V1 that is this, let me substitute it, and I1 into XC where I1 is this. Now we need to simplify this equation of V out in terms of VFB, right? So first of all, I'll be taking VFB common from entire equation, and we need to see how terms are there. So you can observe here we have 1. So this term that we have considered, let me write 1. After that we have 3xc by r. Here we have 3xc by r. So in total we have 6xc by r. So we have considered this and this term. Now here if you observe we have xc square by r square, and here we have xc into 4xc means 4xc square by r square. So in total we have plus 5xc square by r square. So now we have considered these 3 terms and these 2 terms. Now this term is left. So this term is xc cube divided by r cube. Now we have simplified our equation, that is V out is equals to VFB into something, right? Now with this equation we need to understand few basics. So here to understand those basics, first of all we need to substitute value of XC. XC is impedance, that is minus J divided by omega C, right? So I'll be substituting XC is minus J by omega C. So here with this term we will be having minus J into 6 divided by omega R C, plus with this term we have 5 over here, and xc square that is minus square that is positive, then j square that is negative again. So minus 1 will be there over here in numerator, and in denominator omega square c square into r square. And with this term we have xc cube. Xc cube means minus j square, right? So that is minus 1 into minus j, so that will be plus, right? So here we will be having plus j in numerator. In denominator we will be having omega cube c cube into r cube. Now we need to separate real and imaginary part over here. So real part is 1 over here, and here minus 5 divided by omega square c square r square, that is also real part. So let me write it over here. And here we have imaginary part, this and this. So here I need to take plus j common. So I'll be writing this term first and minus of this term. So that is minus 6 divided by omega c into r. Now we have real and imaginary components. One should know with output we don't have imaginary component, means imaginary component over here that is 0. Hence you can say 1 divided by omega cube c cube r cube, that is equals to 6 divided by omega c r. So here omega c r that is getting cancelled. So you can say this omega square that will go on other side, right? That is equals to 1 divided by 6 into c square r square. So based on that you can say omega is equals to 1 divided by c r into square root of 6. And if you wanted to have frequency, then f is equals to 1 divided by 2 pi rc into square root of 6. So that is what the frequency which I have earlier told you regarding RC phase shift oscillator. You see that is the frequency which I have told you earlier, right? That is this for 3 stage of RC combination, right? Now I'll explain you how to have feedback gain. So now for feedback gain we need to have VFB divided by V out, in which this is 0. So this much term is left now. Now with this we need to have feedback gain. So first of all you need to know what is feedback gain. See, feedback gain is VFB divided by V out. Earlier I have told you feedback gain is what? VFB divided by Vout. So if you take that ratio, then feedback gain, that is beta over here. So that will be 1 divided by this term, right? Now in this term, you see 1 minus 5 divided by this is there, right? Now you need to understand this. You see, here I have told you, see 1 divided by omega square c square r square, that is equals to 6. So if you place 1 divided by omega square c square r square, that is equals to 6, then this will be 1 minus 5 into 6. So if you calculate this, then that is 1 divided by 1 minus 30, means it will be minus 1 divided by 29. So feedback gain, that is minus 1 divided by 29. Why minus sign is appearing over here? The reason is there is a phase shift of 180 degree. I have told you earlier, you see, with this circuit, here we have minus sign. The reason is here we have 180 degree of phase shift. Similarly, here gain should be beta, that should be 1 divided by 29, but phase shift should be 180 degree over here, right? So based on phase shift only, we are having beta, that is negative over here, right? So here we have beta, that is 1 by 29, and based on that, we need to select component of RF and R1. If RF divided by R1 is 29, right? In that case, A into beta, that is equals to unity. And based on that, one can have oscillation over here, right? So that is how we can identify all the values, like what is the frequency, that is 1 by 2 pi RC into square root of 6. And how gain beta, that is 1 by 29 over here, along with 180 degree of phase shift. That is what the case which I have derived over here. You can observe over here. I hope you have understood all those things. Still, if anything that you would like to share, please note it down in comment section. I'll be happy to help you. Thank you so much for watching this video.